In 1924, two mathematicians in Poland published a proof that you can take a solid ball, cut it into 5 pieces, and reassemble those 5 pieces into 2 solid balls, each identical to the original. Same size, same density, same everything. No stretching, no adding material, no tricks with definitions. You take the pieces apart, you rotate them through space, you put them back together, and where there was 1 ball, there are now 2. This is not a conjecture. It is not a thought experiment. It is not one of those what-if scenarios that physicists use to illustrate a point before explaining why it cannot actually happen. It is a theorem. It was published in Fundamenta Mathematicae, Volume 6, pages 244 through 277 by Stefan Banach and Alfred Tarski. The paper is titled Sur la décomposition des ensembles de points en parties respectivement congruentes. It has been checked by every generation of mathematicians for 100 years. Nobody has found an error, because there is no error. The proof is valid. The logic is airtight. And its conclusion is that by the rules of the formal system every physicist on Earth uses to describe reality, you can duplicate a solid object using nothing but geometry. And here is what should disturb you. That formal system is not some fringe theory. It is not an alternative mathematics invented by a handful of contrarians. It is ZFC set theory, Zermelo-Fraenkel axioms, plus the axiom of choice. This is the foundation underneath every equation in quantum mechanics, every calculation in general relativity, every model in statistical physics and engineering and economics. When a physicist writes down the Schrödinger equation, they are working inside ZFC. When NASA calculates a trajectory to Mars, ZFC. When the standard model predicts the mass of the Higgs boson to 11 decimal places of accuracy, that prediction rests on ZFC. And ZFC says a ball can become 2 balls. The same rules, the same axioms, the same logical machinery that gives you E equals mc squared also gives you duplication of matter. So either mathematics is wrong, which it is not, because the proof is valid, or physics is incomplete, or the relationship between mathematics and reality is not what you were taught, not what anyone was taught, and not what the scientific establishment wants to talk about publicly. The result has been sitting in the literature for a century without resolution, without a serious research program aimed at explaining the gap, without even a sustained public conversation about what it means. The people who understand it best, the logicians and set theorists who work with these axioms professionally, they do not have an answer. They have preferences. They have philosophical positions they defend at conferences, but they do not have an answer. The theorem is called the Banach-Tarski Paradox, and the question it forces is not how can a ball become 2 balls. That question has a precise technical answer, and you are going to understand it completely. The real question, the one that remains open, is what does it mean that the system humanity built to describe physical law can prove things physical law forbids? What does it mean that the language of nature contains sentences nature cannot speak? And what does it tell you about mathematics itself, that it generated this result not as a bug, but as a necessary consequence of axioms we cannot abandon without crippling physics? The proof is built from 4 steps, each elegant, each unsettling, each importing an algebraic trick into a domain where you would not expect it to work. Start with something called the free group on 2 generators. This is not as intimidating as it sounds. Imagine two operations. Call them A and B. Think of A as a rotation around one axis and B as a rotation around a different axis. Now imagine building every possible sequence from these operations and their inverses. A followed by B. B inverse followed by A followed by B. Every possible finite string, with the rule that an operation immediately followed by its inverse cancels out. The collection of all such strings, together with the rule for combining them, is the free group on two generators. Mathematicians call it F2. This group has a remarkable property. You can partition it into 5 pieces, and those 5 pieces can be rearranged to form 2 complete copies of the entire group. The trick is simple once you see it. Take all the strings that start with A and put them in one pile. All the strings starting with A inverse, another pile. Same for B and B inverse. The identity element stands alone. Now observe that the set of all strings starting with A, when you prepend A inverse to each one, gives you back everything that does not start with A. You recover the whole group from one piece plus a single operation. Do the same with B. You have 2 copies from 5 pieces. That sounds like a game with symbols, and it is. But here is where it stops being abstract. Banach and Tarski realized that 2 specific rotations in 3-dimensional Euclidean space, a rotation by the arccosine of 1/3 around the x-axis and the same angle around the z-axis, generate a subgroup of 3-dimensional rotations that is algebraically identical to the free group F2. The proof that these rotations satisfy no non-trivial relations uses an algebraic argument involving the coordinates of a specific point under all possible sequences of rotations. The point never returns to where it started, no matter what non-identity sequence you apply. The free group is not an invention. It lives inside the rotation group of 3-dimensional space. It was already there, waiting to be noticed. Now you apply these rotations to the surface of a sphere. Every point on the sphere sits in an orbit under the free group action. You apply all possible rotation sequences and trace out the path of each point. The sphere decomposes into uncountably many such orbits, an unimaginably vast number of them, each one a separate track through the surface. And now comes the step that changes everything. You need to pick exactly one representative point from each orbit to serve as a kind of anchor, but there is no formula that tells you which point to choose. There is no algorithm, no rule, no constructive method. The orbits are too numerous and too irregular for any systematic selection. The only way to make all those choices simultaneously is to invoke a very specific axiom, the Axiom of Choice. You invoke it, you build your set of representatives, and then the paradoxical decomposition of the free group maps directly onto the sphere. The sphere splits into pieces that reassemble into 2 complete copies. You handle the center point and a countable number of leftover fixed points with a separate trick involving irrational rotations, bringing the total to 5 pieces. And the thing about those pieces that you need to understand, the thing that separates this from any magic trick or optical illusion, is that they are not pieces in any physical sense. Each piece is what mathematicians call a non-measurable set, an infinite scattering of points distributed across the surface with such pathological complexity that the concept of volume does not apply to them. You cannot say a piece has 0 volume. You cannot say it has positive volume. The question, what is the measure of this piece, has no answer, not because our instruments are not good enough, but because the set exists in a domain of mathematics where the concept of measure breaks down entirely. This is why the duplication does not violate conservation of volume the way you think it should. If you try to add up the volumes of the 5 pieces and show they equal the volume of 1 ball on the left and 2 balls on the right, the calculation never even gets off the ground. Some of the pieces have no volume to contribute. The accounting is impossible. The proof sidesteps the conservation law the way a ghost passes through a wall, not by breaking the rule, but by existing in a category the rule cannot reach. Think about what that means. Mathematics generated objects, these 5 pieces, that provably reassemble into 2 copies of the original. Mathematics also cannot assign those objects a volume. They are real within the formal system. They are theorems, but they are mathematical objects with no physical counterpart whatsoever. Not approximately no counterpart. Not, they are very hard to build. Absolutely no counterpart. They cannot be constructed. They cannot be visualized. They cannot be approximated by any physical process. They exist because an axiom said they could. And this is worth pausing on, because the standard response to Banach-Tarski, the response you will hear from every mathematician who discusses it casually, is that the paradox does not apply to the physical world, because the pieces are not physical objects. That is technically correct, but it misses the point so thoroughly that it almost functions as evasion. The question is not whether you can physically cut a ball into non-measurable pieces. Obviously, you cannot. Atoms are discrete. Matter has a minimum grain size. The question is why the formal system we use to describe all of physics, the system whose predictions we trust to 13 decimal places when calculating the magnetic moment of the electron, generates a proven result that says matter can be duplicated. If the system is reliable enough to build particle colliders and navigate spacecraft to the moons of Jupiter, why does it also prove this? And if it proves this, what else does it prove that we have not checked? What other theorems lurk inside ZFC that flatly contradict conservation laws? Nobody knows. Nobody has conducted a systematic audit. The system is too vast and its consequences are too numerous. We use it on faith, the faith that the outputs relevant to physics will be physically sensible, and the Banach-Tarski Paradox is the proof that this faith is not entirely warranted. There is something deeper here, something you are going to feel building as this goes on. It has to do with what mathematics actually is, whether it was invented by humans or discovered by them, whether it describes reality or merely overlaps with reality in ways we find convenient. The Banach-Tarski Paradox may be the sharpest evidence we have that mathematics is not a mirror held up to nature. It is something else, something larger, something that contains nature's reflection, but also contains images of things nature forbids. And what that means for physics, for the human project of understanding the universe through formal reasoning, is a question that has been open for a century with no answer in sight. And that axiom, the axiom of choice, is what the rest of this story is about. Because when you pull on this thread, what unravels is not a single paradox, but 100-year fracture in the foundations of human knowledge. And the people who discovered that fracture paid for the discovery with their careers, their sanity, and their lives. The axiom of choice says something that sounds, on first hearing, so obvious it barely seems worth stating. If you have a collection of non-empty boxes, you can always form a new set by picking exactly one item from each box. For finite collections, nobody questions this. You have 3 boxes, you reach in 3 times, done. But the axiom does not restrict itself to finite collections. It says you can make selections from infinitely many boxes simultaneously, even uncountably many, even when there is no rule or pattern or algorithm telling you which item to pick from which box. It asserts the existence of a completed selection without any method for performing it. Bertrand Russell gave the famous illustration. You can always select from an infinite collection of shoes, he said, because you can specify a rule. Take the left shoe from each pair. But an infinite collection of socks, where the 2 in each pair are identical, requires the axiom of choice. There is no canonical rule for choosing between identical objects. The axiom says you can do it anyway. When Ernst Zermelo formally proposed this axiom in 1904, the mathematical world did not respond with polite, scholarly debate. It erupted. Zermelo had used the axiom to prove the well-ordering theorem, which says every set can be arranged in a sequence where every subset has a smallest element. This includes the real numbers, which as far as anyone knew, had no natural ordering of that kind. The idea that you could well order the continuum struck many mathematicians as absurd, and the tool Zermelo used to prove it, the axiom of choice, struck them as illegitimate. The most revealing exchange happened in 1905, when 4 of France's greatest mathematicians traded a series of letters that became one of the most important philosophical documents in the history of mathematics. René Baer, Émile Borel, Jacques Hadamard, and Henri Lebesgue argued about the nature of mathematical existence itself. Hadamard, and Hadamard alone, defended the axiom fully. He drew a distinction between defining a mathematical object and naming it. An object can exist, he argued, even if we have no procedure for constructing or pointing to it. Borel rejected the axiom for uncountable collections. Lebesgue wrote the most nuanced response, arguing that to choose from infinitely many sets, one must provide a law of selection, because life is too short to name the elements one by one. The brutal irony surfaced years later. Wacław Sierpiński demonstrated that Lebesgue himself had used the axiom of choice without acknowledging it in his proof that countable unions of Lebesgue measurable sets are measurable, GH. Hardy showed that Borel had unconsciously relied on it for an uncountable indexing set in one of his own results. The mathematicians who rejected the axiom had been standing on it the entire time. They were demolishing a load-bearing wall from the second floor. This is the thing about the axiom of choice that makes the whole debate so destabilizing. It is not an exotic axiom bolted onto the side of mathematics. It is woven into the fabric of results that every mathematician uses without thinking. You use it when you claim that the union of countably many countable sets is countable. You use it when you assert that every filter can be extended to an ultrafilter. You use it in weaker forms when you do basic analysis. The axiom hides in the background of proofs the way gravity hides in the background of a building's structural integrity. You do not notice it until someone points out that it is there, and then you realize it is holding up everything. The deeper problem, the one the 5 French letters were really arguing about, even if they did not frame it this way, is the question of mathematical existence. When Hadamard said a mathematical object can exist without being explicitly defined. He was staking a philosophical position that most working mathematicians now share, but cannot justify from within mathematics itself. The axiom of choice says these selection sets exist. It does not say how to build them. It does not provide instructions. It asserts existence without construction. And the question that should keep you up at night is, what does existence mean in mathematics? If a set exists but cannot be described by any formula, cannot be computed by any algorithm, cannot be specified by any finite procedure, in what sense is it real? Platonists say it is real because mathematical objects exist independent of human minds. Formalists say the question is meaningless because mathematics is just symbol manipulation. Constructivists say the set does not exist because existence requires a construction. And the formal system says, I don't care about your philosophy. The axiom is consistent. The set exists. Here is a theorem. The Banach-Tarski pieces are exactly this kind of object. They exist by fiat. They are the logical consequences of an axiom that asserts the possibility of making uncountably many arbitrary choices simultaneously. No one has ever seen a non-measurable set. No one ever will. And yet, the formal system treats them as fully real as the number 2 or the set of prime numbers, and derives theorems about them with the same certainty it brings to any other mathematical truth. And here is where Alfred Tarski re-enters the picture, and the mathematics becomes inseparable from the human tragedy running underneath it. Tarski was born Alfred Teitelbaum on January 14th, 1901, in Warsaw. He and his brother changed their surname to Tarski in 1923. They invented the name because it sounded Polish, was simple, and was not being used by anyone. They simultaneously converted to Roman Catholicism, despite Alfred being an outspoken atheist for his entire life. The motivation was not spiritual. Anti-Semitic policies in interwar Poland made it effectively impossible for a Jew to obtain a university chair. The reinvention was a survival strategy. Tarski proved that the axiom of choice is logically equivalent to the statement that for any infinite set X, there exists a bijection between X and X times X. He submitted this result to the French journal Comptes Rendus. Maurice Fréchet rejected it because an implication between two well-known propositions was not a new result. Henri Lebesgue rejected it because an implication between two false propositions was of no interest. Think about that. The axiom that made Tarski's most famous theorem possible was being dismissed by the very people who had unconsciously depended on it in their own work. Tarski never submitted to that journal again. On August 11th, 1939, Tarski boarded the SS Pilsudski from Warsaw, bound for a Unity of Science Congress at Harvard. It was the last ship to leave Poland for America before the German invasion. He carried a small suitcase, money for a few weeks, and summer clothing, expecting to return shortly. The Pilsudski was torpedoed on its return voyage. Tarski arrived in New York on August 22nd and heard the news of the German-Soviet non-aggression pact. Because he had publicly converted from Judaism, the Polish-Jewish diaspora shunned him. He was isolated. He could not get his family out. His parents, his brother, and his sister-in-law were all murdered in the Holocaust. His wife Maria and 2 young children survived the entire occupation in Warsaw, including the 1944 uprising, and were finally reunited with him in Berkeley in January 1946, but the marriage was destroyed. The children eventually became estranged. The man who proved a ball could become two balls could not hold his own family together across the distance the war created. But the axiom of choice does not only enable the Banach-Tarski paradox, it systematically generates an entire category of mathematical objects that cannot exist in the physical universe, non-measurable sets. And once you understand what they are, the paradox stops seeming like an isolated curiosity and starts looking like a symptom of something much deeper. Giuseppe Vitali published the first non-measurable set construction in 1905. Take the real numbers between 0 and 1. Define two numbers as equivalent if their difference is a rational number. So 0.3 and 0.3 plus 1/7 are equivalent because 1/7 is rational. 0.3 and 0.3 plus pi are not equivalent because pi is irrational. This equivalence relation partitions the interval into uncountably many classes, each one a cloud of points separated from each other by rational distances. Every class is infinite. There are uncountably many classes, and they tile the interval perfectly, every real number sitting in exactly one class. Now use the axiom of choice to select exactly one representative from each class. Call this collection V. You are picking one point from each of uncountably many clouds. There is no formula for this selection, no algorithm, no procedure that a computer could execute. The axiom of choice simply asserts that the completed selection exists. Consider all rational translates of V, that is, all sets formed by shifting V by every rational number between -1 and 1. These translates are pairwise disjoint. Their union covers the interval from 0 to 1 and fits inside the interval from -1 to 2. Now try to assign V a measure. If V has measure 0, then countably many copies of it, all with measure 0, have a union with measure 0. But that union covers the interval from 0 to 1, which has measure 1. Contradiction. If V has positive measure, then countably many copies of a set with positive measure have a union with infinite measure. But the union fits inside an interval of length 3. Contradiction. V has no consistent measure, not 0, not positive, not anything. It is unmeasurable. It is a set that the machinery of integration and probability and physical measurement cannot touch. The Banach-Tarski pieces are sets like this. And this is why the paradox works. If the 5 pieces had well-defined volumes, you could add them up. They would need to sum to the volume of one ball when arranged one way and 2 balls when arranged the other way. 1 equals 2. Impossible. But the pieces do not have volumes. The addition never happens. The contradiction never forms. The duplication proceeds unimpeded through a gap in the concept of measurement itself. Robert Solovay proved in 1970 that in a model of set theory, without the axiom of choice, assuming the consistency of an inaccessible cardinal, every subset of the real numbers is Lebesgue measurable. Without choice, non-measurable sets do not exist. The pathological objects disappear. The ghosts vanish. The Banach-Tarski paradox evaporates. But there are even more non-measurable sets than measurable ones. This is not an exaggeration or a metaphor. In ZFC, the cardinality of the collection of Lebesgue measurable subsets of the real line is 2 to the power of the continuum, the same as the total number of subsets. But the measurable sets form a sigma algebra, a structured, well-behaved collection, while the non-measurable sets are everything else. They are the generic case. The typical subset of the real line, if you could somehow pick one at random, would be non-measurable. Measurability is the exception. The well-behaved sets that underpin all of applied mathematics, all of probability, all of physics, are a special case within a sea of pathological objects that the axiom of choice guarantees, but that no physical process can instantiate. The foundation of mathematical physics is built on an island in an ocean of impossibility, and the axiom that creates the island also creates the ocean. And yet, we keep the axiom. We keep it because the cost of removing it is unacceptable. Without the axiom of choice, you lose Zorn's lemma, which guarantees the existence of maximal ideals in algebra and is invoked constantly in ring theory, field theory, and abstract algebra. You lose the guarantee that every vector space has a basis, a fact so fundamental that most mathematicians use it without even thinking about it. You lose Tychonoff's theorem in its general form, which says that any product of compact topological spaces is compact, a cornerstone result in topology used in functional analysis, algebraic geometry, and mathematical physics. You lose the Hahn-Banach theorem in its full generality, which underpins the entire field of functional analysis, and therefore the mathematical foundations of quantum mechanics. You lose the fact that every connected graph has a spanning tree. You lose the comparability of cardinal numbers, meaning you can no longer prove that any two sets can be compared in size. You lose Godel's completeness theorem for first-order logic. The list goes on. Almost every branch of mathematics above the level of basic calculus has results that depend, somewhere in the chain of proof, on the axiom of choice. Jerry Boner captured the dilemma in a joke that has been circulating among mathematicians for decades. The axiom of choice is obviously true, the well-ordering principle is obviously false, and who can tell about Zorn's lemma? The humor lies in the fact that all three statements are logically equivalent. If you accept any one of them, you must accept all three. The axiom of choice feels like common sense. The well-ordering principle says the real numbers can be arranged so that every subset has a smallest element, which feels impossible. Zorn's lemma is so abstract that most people cannot even pass it on first reading, and they are all the same statement, wearing different masks. Now, behind all of this, behind the axiom and the non-measurable sets and the paradoxical decomposition, there is an older story, because none of this would exist without the man who invented the framework of infinite set theory itself. And what happened to him is a warning about what it costs to look too closely at the foundations. Georg Cantor was born in 1845 in St. Petersburg and spent most of his career at the University of Halle, a provincial institution far from the centers of mathematical power. In the 1870s, he proved something that shattered the mathematical consensus about infinity. He showed that different sizes of infinity exist. The rational numbers, though infinite, can be listed in a sequence paired 1-to-1 with the natural numbers. You can literally write them all down in order if you are clever about it. The real numbers cannot be listed this way. There are strictly more real numbers than rationals. There are more points on a line segment than there are counting numbers. He proved this first indirectly in 1874, and then with devastating simplicity in 1891. using the diagonal argument, a proof technique so elegant and so destructive that it can be explained to a bright 12-year-old and has resisted every attempt at refutation for over a century. And then he went further. He showed there is no largest infinity. For any infinite set, the set of all its subsets, the power set, is strictly larger, an endless hierarchy of infinities, each one inconceivably dwarfing the last, spiraling upward without limit. He called these transfinite cardinal numbers and built an arithmetic for them, rules for adding and multiplying infinities that were as rigorous as ordinary arithmetic. He proposed the continuum hypothesis, the conjecture that there is no infinity between the countable and the continuum, and spent decades trying to prove it. He failed. That failure became the first problem on David Hilbert's famous list of 23 unsolved problems presented at the 1900 International Congress of Mathematicians. It would not be resolved until Cohen's forcing technique in 1963 showed it, like the axiom of choice, to be independent of ZF, undecidable, neither provable nor disprovable. Cantor could not have known that the question he was killing himself trying to answer had no answer within the system. His former teacher, Leopold Kronecker, declared war. Kronecker called Cantor a scientific charlatan, a renegade, a corrupter of youth. He publicly declared that God made the integers and all else is the work of man, a statement aimed directly at Cantor's transfinite numbers. Kronecker used his position at the University of Berlin to block Cantor from ever obtaining a chair there. Henri Poincaré called set theory a grave disease infecting the body of mathematics. Cantor spent decades trying to prove the continuum hypothesis, his conjecture about whether there exists an infinity between the countable and the continuum, and failed. The failure tormented him. His first recorded depressive episode came in 1884. All 52 letters he wrote to Mittag Leffler that year mentioned Kronecker. In 1899, Cantor's youngest son, Rudolf, died suddenly while Cantor was away delivering a lecture. Modern scholars believe Cantor suffered from bipolar disorder. The attacks on his work did not cause the illness, but they appear to have triggered and worsened the episodes. On January 6, 1918, Georg Cantor died of a heart attack in the Halle Nervenklinik, a psychiatric institution where he had been admitted against his will, where he spent his final year writing letters to his wife, begging to come home. He was malnourished due to wartime food shortages. David Hilbert later issued the statement that has become Cantor's epitaph: "No one shall expel us from the paradise that Cantor has created for us." But Cantor himself had been expelled from everything. The man who revealed the architecture of infinity died locked in a building he could not leave, starving and alone. And then there is Felix Hausdorff. If Cantor built the foundations, Hausdorff built the first structure on top of them, and the structure he built was the direct precursor to Banach-Tarski. In 1914, Hausdorff proved what is now called the Hausdorff paradox. He showed that the surface of a sphere, after removing a countable set of points, could be decomposed into three disjoint sets, A, B, and C, all congruent to each other under rotations, with A also congruent to the union of B and C. One piece is the same size as two pieces combined. The sphere minus a handful of points is paradoxical. Banach and Tarski's contribution was to extend this from the sphere to the solid ball. to handle the leftover points and to prove the far stronger result that any two bounded sets with non-empty interior are equide composable. Hausdorff lived a double intellectual life. Under his own name, he published the 1914 Grundzüge der Mengenlehre, which essentially founded general topology as an independent discipline. Under the pseudonym Paul Mongret, from the French à mon gré, meaning according to my taste, he was a celebrated author of Nietzschean philosophy, aphorisms, and satirical plays. His play, Der Arzt seiner Ehre, was performed over 300 times in 31 German cities. After the Nazi seizure of power in 1933, Hausdorff was forced into retirement in 1935 under the Nuremberg laws. After Kristallnacht in November 1938, he applied for a research fellowship to emigrate to the United States. At 71, he was not a priority for the rescue committees. The application went nowhere. Through 1930, 1940, 1941, the walls closed in. In mid-1941, the Jews of Bonn began receiving deportation orders to an internment camp at Endenich, on the outskirts of the city. On January 25, 1942, Felix Hausdorff, his wife Charlotte, and her sister Edith Pappenheim received their orders. That night, all three took lethal overdoses of Veronal. In his farewell letter to his lawyer friend, Hans Wallstein, Hausdorff wrote that by the time Wallstein read the lines, they three would have solved the problem in another way, the way Wallstein had continually tried to dissuade them from. He wrote that what had been done against the Jews in recent months aroused well-founded anxiety that they would no longer be allowed to experience a bearable situation. He asked forgiveness for their desertion. He wished his friends better times. In a separate note, Hausdorff wrote a line that is either the bleakest pun in the history of mathematics or a small act of defiance against meaninglessness. Auch Endenich ist noch vielleicht das Ende nicht. Perhaps Endenich is not yet the end, a play on the district's name. Endenich was also where Robert Schumann spent his last years in an insane asylum. The letter was addressed to Hans Wallstein. Wallstein was later murdered at Auschwitz. The letter itself disappeared for decades. In 2012, an archivist at the University of Bonn discovered it on a stack of empty leaflets during a routine inspection of uncatalogued materials. For 70 years, the last words of one of the 20th century's greatest mathematicians had been sitting unread in a drawer. The man who first proved you could paradoxically rearrange a sphere chose the most permanent rearrangement available to him, and the mathematics he left behind kept generating consequences he never lived to see. Here is something that becomes unavoidable once you know these stories. The mathematics that Cantor, Hausdorff, Banach, and Tarski created was not just a professional accomplishment. It was, for each of them, the central axis of their existence. Cantor staked his sanity on the reality of transfinite numbers. Hausdorff staked his identity on the life of the mind in a world that was systematically destroying Jewish intellectual life. Banach staked everything on a discipline he was not formally credentialed to practice. Tarski staked his survival on reinventing himself completely. And the mathematics they produced, this framework of sets and axioms and infinite decompositions, outlived all of them and continued generating truths that none of them anticipated. The Banach-Tarski Paradox is one of those truths. But the deeper point is that the formal system seems to have a trajectory of its own. It does not care about the people who build it. It does not care about their intentions. They wanted to understand infinity, to formalize measurement, to create a rigorous foundation for analysis. What they got was a system that proved you can duplicate a solid sphere, a result that none of them would have endorsed as describing anything real. The system exceeded what its creators meant for it to do, and it did so using axioms they chose for reasons of mathematical convenience, not physical correspondence. Mathematics appears to have a life independent of the mathematicians who practice it, and some of what it produces on its own is not compatible with the universe those mathematicians inhabit. Because the Banach-Tarski paradox does not work in one dimension, it does not work in two dimensions, it works specifically in three or more dimensions, and the reason is not a technicality. It is one of the deepest structural facts about the geometry of the space you live in. John von Neumann explained why, in 1929, he introduced the concept of amenable groups, a term actually coined later by Malandé in 1957 as a probable pun on meanable, meaning admitting an invariant mean. A group is amenable if you can assign a consistent notion of size to all its subsets in a way that respects the group's symmetries. The essential fact is this: in 1 and 2 dimensions, the groups of rigid motions are solvable, and solvable groups are amenable. Banach himself proved in 1923 that a finitely additive translation invariant measure exists for all bounded subsets of the line and the plane. In these dimensions, paradoxical decompositions are impossible because any rearrangement of pieces must preserve their total measure. The books always balance. But in 3 dimensions, the rotation group SO3 is different. It is non-abelian and non-solvable. More importantly, it is rich enough to contain a free subgroup on 2 generators. Those 2 rotations by Arcosine of 1/3 that I mentioned earlier, they generate a copy of the free group F2 sitting inside SO3, and F2 is non-amenable. There is no consistent way to assign size to all of its subsets. Tarski later proved the converse as well. A group admits a paradoxical decomposition if and only if it is non-amenable. The chain is complete. 3-dimensional rotations contain a free group. Free groups are non-amenable. Non-amenable groups admit paradoxical decompositions. 3-dimensional space is paradoxical, and you live in 3-dimensional space. The specific dimensionality of the universe you inhabit is precisely the minimum dimensionality at which mathematical truth and physical law diverge. If the universe had 2 spatial dimensions, the Banach-Tarski paradox could not exist. Mathematics and physics would agree about what is possible. The fact that they disagree is a consequence of the particular geometry we actually have, not of infinity being strange, not of axioms being controversial, of the specific structure of rotations in 3-dimensional Euclidean space. Your universe is built at the exact dimensionality where the foundations crack. Now, there is a misconception about Banach-Tarski that has become standard in popular treatments, and it needs to be corrected because it obscures the real significance of the result. The standard framing is that Banach-Tarski is just infinity being weird, that it is a consequence of the strangeness of infinite sets, and we should not be surprised when infinity produces counterintuitive results. This is wrong. Banach-Tarski is not a generic consequence of infinity. It requires three very specific things interacting in a very specific way. The axiom of choice, which generates non-measurable sets, the structure of three-dimensional rotations, specifically the existence of a free subgroup in SO3, and the framework of Lebesgue measure, which assigns volumes to sets in a way that is invariant under rigid motions. Remove any one of these three ingredients, and the paradox collapses. Without the axiom of choice, the non-measurable pieces cannot be constructed. Without three dimensions, the rotation group is too simple to contain a free subgroup. Without the measure-theoretic framework, the rearrangement produces no contradiction. It is not infinity being strange. It is a precision instrument probing a specific fault line in the interaction between algebra, geometry, and analysis. A fault line that runs directly under mathematical physics. There is a second misconception that is even more damaging, and it is the one reinforced by the popular treatments that brought Banach-Tarski to a mass audience. The Vsauce video from 2015 reached tens of millions of viewers. It is well produced and communicates the shape of the paradox effectively, but it never names the axiom of choice explicitly, and it leaves the viewer with the impression that this result has been explained, that it is understood, that mathematicians have filed it under interesting but resolved and moved on. This is not true. The proof is well understood technically. Nobody disputes it. But what it means for the relationship between mathematics and physical reality has never been resolved. There is no philosophical framework, no meta-theorem, no principle that explains why ZFC generates this result and also generates the equations that predict experimental physics to extraordinary precision. The standard response in mathematics departments is that the paradox shows physical intuition is unreliable in mathematical contexts. Fine, but the mirror image is equally valid and equally unaddressed. The paradox shows that mathematical truth is not a reliable guide to physical possibility, and nobody has drawn the line between the truths that correspond to reality and the ones that do not. Nobody has even proposed a method for drawing that line. Stefan Banach, whose name is on the theorem, had a life built from the same impossible materials as his proof. He was born on March 30th, 1892, at St. Lazarus General Hospital in Krakow, born out of wedlock. His father, Stefan Banach, was a soldier whose military rank prohibited marriage. His mother's identity remains unknown. She is listed on the birth record as Katarzyna Banach. His father told him he had sworn an oath of secrecy about her identity and kept the secret until his death in 1967, at nearly 100 years old. The infant was given to Franziska Plauer, a laundress and laundry business owner, to be raised. Banach never had a conventional family and never earned a formal university mathematics degree. The story of his discovery is one of the most remarkable accidents in the history of science. On a summer evening in 1916, Hugo Steinhaus, an established mathematician trained under David Hilbert at Göttingen, was walking through Krakow's Planty Gardens when he overheard two young men on a park bench discussing Lebesgue measure, the Lebesgue integral, a subject so advanced and so new at the time that hearing it discussed casually in a public park was like stumbling onto two strangers debating the technical specifications of a classified weapons system. Steinhaus introduced himself. One of the young men was Stefan Banach. Steinhaus posed a problem he had been struggling with. Within days, Banach returned with a complete solution. The result became their first joint publication. Steinhaus later said that Stefan Banach was his greatest scientific discovery. Banach's doctoral thesis, completed between 1920 and 22, without him ever having graduated from university, axiomatically defined what are now called Banach spaces and is sometimes cited as the founding document of functional analysis. The same year he received his doctorate, he was co-authoring the paper with Tarski that would become his most famous result. The collaboration was unusual. Banach was in Lwów, Tarski in Warsaw. They came from different mathematical traditions, different backgrounds, different worlds. Banach was the self-taught orphan who thought in terms of spaces and measures. Tarski was the logician who thought in terms of formal systems and truth. Together they combined analysis and set theory in a way that produced a result neither could have reached alone. And neither of them, as far as the historical record shows, expected the result to have the philosophical significance it turned out to carry. They published it, moved on to other problems, and left the paradox sitting in the literature like a mathematical time bomb. Banach created the Lwów School of Mathematics, an extraordinary concentration of talent centered on the Scottish Café, a coffee house where mathematicians gathered daily to work on problems scribbled on marble tabletops. The atmosphere was legendary. Problems were posed and solved between rounds of coffee and vodka. Bets were placed. Prizes were offered. When the owner complained about the mess and Banach's wife Lucia grew tired of proofs being wiped away by waiters, she purchased a large notebook and left it with the proprietor. It became the Scottish Book, eventually containing 193 problems contributed by Banach, Steinhaus, Stanislaw Ulam, Stanislaw Maza, and others. The prizes ranged from 5 glasses of beer to, in one memorable case, a live goose offered by Mazur for the solution to problem 153, posed in 1936. The goose was actually awarded in 1972 to Per Enflo, a Swedish mathematician who solved the problem of whether every separable Banach space has a Schauder basis. The answer was no. The ceremony was broadcast on Polish television. Mazur, then 87 years old, personally handed over the goose. During the Nazi occupation of Lwów, Banach survived by working as a feeder at Rudolf Weigel's Typhus Research Institute. Cages of typhus-infected lice were strapped to workers' calves, and the lice fed on human blood for about an hour each day. The job provided identity documents noting that the holder might carry typhus, which the Gestapo feared enough to leave those workers alone. Wacław Cybalski, who supervised the feeding unit, remembered that it was intellectually stimulating, if surreal, to listen to the mathematicians discussing the frontiers of topology and number theory, while lice fed on their blood. Antoni Lomnicki, Banach's own doctoral supervisor, was shot during the massacre of Lwów professors in July 1941, along with approximately 40 other Polish academics and their families. Banach died of lung cancer on August 31st, 1945, at 53 years old, months before he was to take up his new chair in Krakow. His funeral at Lichakiew Cemetery became an impromptu patriotic demonstration by the Poles still remaining in the city. Among his many results, his name survives most prominently attached to a theorem he co-authored about cutting balls into impossible pieces. He would probably have found that fact amusing and slightly absurd. The man who proved you could get 2 from 1 could not get himself enough years to fill a single normal lifespan. But the theorem will outlive every city he lived in, every institution that employed him, every nation whose borders shifted around him while he worked. It is, in its way, the most permanent thing any of them produced, a mathematical truth that does not decay, does not age, does not depend on the survival of the civilization that produced it. It is true now and will be true after the last human being is gone. And it says something about reality that reality itself does not permit. Now, if the axiom of choice is the mechanism that makes Banach-Tarski possible, the obvious question is whether the axiom is true. And the answer to that question is the most deeply disturbing part of this entire story. In 1938, Kurt Godel proved that the axiom of choice is consistent with the other axioms of set theory. If ZF, the axiom system without choice, does not produce contradictions, then ZFC, the system with choice, does not produce contradictions either. You cannot disprove the axiom of choice from within the standard framework. The method Godel used introduced the constructible universe, designated L, an inner model of set theory where every set is built layer by layer from definable operations. Within L, the axiom of choice and the continuum hypothesis both hold. Godel was not proving that the axiom was true. He was proving that it was safe, that adding it to the other axioms would never lead to a contradiction. You could use it without fear of blowing up the system. The mathematical establishment breathed easier, even though the question of the axiom's truth remained wide open. In 1963, Paul Cohen proved the opposite direction. Cohen was not a logician by training. He was an analyst, a 29-year-old at Stanford who had decided to attack the biggest open problem in the foundations of mathematics, essentially as an outsider. Using a revolutionary technique he invented called forcing, Cohen constructed models of set theory in which the axiom of choice fails. Forcing works by carefully extending a model of set theory, adjoining new generic sets that are designed to violate whatever statement you want to disprove. It is one of the most powerful techniques in all of modern mathematics, and Cohen invented it from scratch. His result established that the axiom is independent of ZF. You cannot prove it from the other axioms, and you cannot disprove it. It floats in a permanent logical limbo, true in some models, false in others, undetermined by the axioms that most mathematicians consider fundamental. Godel reviewed Cohen's proof and sent him a letter that mathematicians still quote. He wrote that in all essential respects, Cohen had given the best possible proof, and that this does not happen frequently, and that reading the proof had a similarly pleasant effect on him as seeing a really good play. Cohen received the Fields Medal in 1966, the only Fields Medal ever awarded for work in mathematical logic. Together, Godel and Cohen proved that mathematics cannot decide whether the axiom of choice is true. It is not that we have not figured it out yet. It is that the question is undecidable within the system. Mathematics cannot police its own boundaries. It cannot determine which of its axioms correspond to reality and which generate phantoms. You choose to accept the axiom of choice, or you choose not to. Both choices produce internally consistent but fundamentally different versions of mathematics. In one version, a ball can become two balls. In the other, it cannot. Both are valid. Godel himself was a Platonist. He believed mathematical objects exist independently of human minds, that the axiom was objectively true, even if it could not be formally proved. that the inability to prove it was a limitation of the formal system, not of reality. His conviction about the independence of mathematical truth from human cognition was absolute. His relationship with physical reality was not. Godel suffered from lifelong paranoia about being poisoned. He would eat only food prepared by his wife Adele. In 1970, Adele was hospitalized after a stroke. Godel refused to eat. He was admitted to Princeton Hospital on December 29th. On January 14th, 1978, Kurt Godel died. He weighed 65 pounds. The death certificate listed the cause as malnutrition and inanition caused by personality disturbance. The man who proved the axiom of choice was safe within mathematics could not trust the physical world to be safe for him. Cohen's result was supposed to settle the question. It did the opposite. It proved the question unsettlable. The axiom is neither mandatory nor forbidden, and the version of mathematics that every working physicist uses every day in every equation is the version with the axiom included. ZFC. The C stands for choice, and here is where everything converges and the full weight of what you have been learning becomes inescapable. Because the independence of the axiom of choice is not just a technical curiosity about the limits of formal proof. It means mathematics cannot police its own boundaries. It cannot determine from the inside which of its axioms generate truths about the physical world and which generate phantoms. The formal system is flying blind. It produces theorems, billions of them, an unending cascade, and some of those theorems correspond to physical reality with breathtaking precision, and some of them say you can duplicate a solid ball, and the system itself has no mechanism for sorting the two categories apart. We are relying on a tool that cannot distinguish its own real outputs from its own impossible ones, and we know this. We have known it for 100 years. And we keep using the tool because there is nothing else. In 1960, the physicist Eugene Wigner published a paper in Communications in Pure and Applied Mathematics titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He noted that mathematical structures developed for purely abstract reasons turn out to describe physical phenomena with extraordinary precision, and called this a wonderful gift which we neither understand nor deserve. Wigner was right. The effectiveness of mathematics is unreasonable. Equations written to solve abstract problems in the 1800s turned out to describe the behavior of black holes. Group theory, developed as pure algebra, turned out to classify elementary particles. The correspondence between mathematical structure and physical law is shockingly deep and has no satisfying explanation. The Banach-Tarski Paradox is Wigner's miracle in reverse. It is a case where the unreasonable effectiveness breaks down completely, where a proven theorem of mathematics does not merely fail to correspond to physical reality, but actively contradicts it. Conservation of mass, conservation of volume, the basic principles that say you cannot create something from nothing, are violated by a valid proof within the very system physicists use to express those principles. And nobody can explain why mathematics is unreasonably effective in some domains and unreasonably hostile in others. There is no boundary between the two behaviors. There is no warning. The same axioms produce both outputs with equal confidence and equal rigor. Richard Feynman captured this in an anecdote about arguing with mathematician friends. They would explain the result to him. You have an orange, you cut it into finitely many pieces, you put it back together, and it is as big as the sun. True or false? True, they told him. And Feynman would reply, but you said an orange. You cannot cut the orange peel any thinner than the atoms. His point was precise. The theorem concerns the mathematical continuum, not discrete physical matter. But Feynman's objection, correct as it is, does not dissolve the problem, it sharpens it. If the continuum model is accurate enough to build nuclear reactors and predict the magnetic moment of the electron, why does it also support the duplication of matter? The model works where we need it and breaks where we do not expect it, and we have no theory for where the line falls. There is an alternative axiom, the axiom of determinacy, proposed by Misielski and Steinhaus in 1962. It concerns infinite two-player games where players alternately choose natural numbers and one player wins if the resulting sequence falls in a given set. The axiom of determinacy says one player always has a winning strategy. It is incompatible with the full axiom of choice, but under it, every subset of the real numbers is Lebesgue measurable. Non-measurable sets do not exist. Banach-Tarski vanishes. Mathematics becomes tame. But without the axiom of choice, you cannot do modern physics. The Hahn-Banach theorem, Tychonoff's theorem, the existence of bases for vector spaces, the entire apparatus of functional analysis that underpins quantum mechanics, all of it requires the axiom of choice. The alternative mathematics is cleaner. It is more physically intuitive, and it is too weak to describe the physical universe. You cannot have both. You can have a mathematics that agrees with physical intuition about conservation and measurement, but that cannot support quantum mechanics or general relativity. Or you can have a mathematics powerful enough to describe the actual physical universe, but that contains proven theorems violating the physical laws it is used to describe. Those are the two options. There is no third. This has been the situation for 100 years, and there is no indication it will change. Think about what this means practically. Every time a physicist writes down a wave function, they are working inside a system that says a ball can become two balls. Every time an engineer calculates the load-bearing capacity of a bridge using calculus built on Lebesgue integration, which rests on measure theory, which assumes ZFC, they are using the axioms that guarantee the existence of non-measurable sets. Every GPS satellite, every MRI machine, every quantum computer prototype relies on mathematics that includes, as a proven theorem, the duplication of solid objects. The impossible result and the functional result share the same axioms, the same logical foundation, the same formal system. They are siblings, and nobody can explain why one sibling describes reality while the other violates it. The mathematician Raphael Robinson proved in 1947 that exactly 5 pieces is the minimum needed for the ball duplication. Not 6, not 4, 5. The proof is constructive in the sense that the decomposition procedure is explicit, even though the pieces themselves are non-constructive, requiring the axiom of choice for their existence. Randall Doherty and Matthew Foreman proved in the early 90s that the decomposition can be carried out with pieces having the property of Baire, a topological regularity condition, which shattered the assumption that the pieces must be maximally pathological. And in 1990, Miklos Lachkovich resolved a related problem that had been open since 1925. He showed that a circle can be cut into finitely many pieces and rearranged into a square of equal area. The number of pieces required was approximately 10 to the 50th power, 10 followed by 50 zeros, all non-measurable, all requiring the axiom of choice. Stan Wagon called the result jaw-dropping. Even more remarkably, Andrew Marks and Spencer Unger achieved a constructive version of this result in 2017 using Borel pieces requiring no axiom of choice at all. The field keeps moving, but the central problem, the gap between mathematical truth and physical reality, does not move. It sits exactly where Banach and Tarski left it in 1924. And so you are left with what the title promised. You can mathematically prove something that is physically forbidden. The proof is correct. It has been correct since 1924. And the gap it reveals between mathematics and physical reality has no name, no research program, no resolution, and no prospect of one. Mathematics is not a description of reality. That is the thing nobody told you. The thing the popular accounts of science leave out. The thing working physicists know at some level but never discuss publicly because there is nothing productive to say about it, and saying it out loud would undermine the authority of the tool they depend on. Mathematics is a formal system that humans constructed to describe reality, and at some point in the late 19th and early 20th centuries, it exceeded its mandate. It kept generating truths. Some of those truths, like Maxwell's equations predicting electromagnetic waves before anyone observed them, were gifts, unreasonable, unexplained gifts that told us something true about the universe before we had the technology to verify it. And some of those truths, like the Banach-Tarski Paradox, are the opposite of gifts. They are proven statements within the same system that say things the universe does not allow. And the system treats both categories with identical rigor, identical certainty, identical formal validity. The formal system broke free of the physical world it was designed to model. It kept going. It wandered into territory where the laws of physics do not follow. And the version of mathematics that wandered, the one that contains the impossible theorems alongside the functional ones, is the only version powerful enough to do physics. The tame version, the one without the axiom of choice, the one where every set is measurable and Banach-Tarski vanishes and conservation laws are never violated, is too weak. It cannot support quantum mechanics. It cannot support functional analysis. It cannot support the mathematics of the physical world. We are trapped in a formal system that is simultaneously indispensable and untrustworthy. We need it to describe the universe, and it describes things the universe forbids. Both of these facts are proven. Both are beyond dispute, and no one, in 100 years of trying, has found a way to reconcile them. Wigner asked why mathematics is so unreasonably effective. That is the famous question, the comfortable one. The Banach-Tarski Paradox poses the uncomfortable question, the one nobody wants to stand behind a podium and ask out loud. Why is mathematics unreasonably effective most of the time, and then, with the same axioms, the same logic, the same rigor, prove something that annihilates physical law? What separates the mathematics that describes the universe from the mathematics that describes things the universe does not allow? Nothing. Nothing separates them. There is no formal principle, no meta-theorem, no criterion from within mathematics or from within physics that draws a line between the two. Physicists navigate by instinct an experiment. They use the results that match observation and quietly set aside the ones that do not. This works pragmatically in the way that crossing a frozen lake works. You get to the other side, but only if you never look down. The calculations have been checked. The proof is what it is. A solid ball can be cut into 5 pieces and reassembled into 2 identical copies of itself. The pieces have no volume, no physical existence, no constructive definition. They exist because an axiom allows infinitely many simultaneous choices without a rule. We accepted that axiom because we had to. We had to because without it, our mathematics cannot describe the universe we live in. And with it, our mathematics describes things this universe does not permit. That is where it stands. That is where it has stood for a century, and nobody can explain why.